So, when last we talked, we were talking about J.J. Thomson and his plum pudding model of the atom. So, he surmised that there was the positive pudding sort of stuff, and then within that were studied the negative electrons. So, today we're going to talk first about Ernest Rutherford, who was another chemist around the same time. And his goal was really to lend support and credence to J.J. Thomson's model. He really felt like that was the shape of the atom, and so he wanted to design a way to sort of not prove that was true, because we don't do that, but really to add support to Thomson's model. So, you can see here a couple of pictures that kind of show what Rutherford set out to do. He wanted to try to use an indirect method, like in the Marble Lab, to determine what the atom actually looked like. So look at these two pictures just for a second and see if you can figure out the shape of the target beneath them. You can pause for a second if you need to. Then I'm going to show you the answer. So here you can see the end result. What Rutherford wanted to try to do was to come up with a way where he could look at the input and look at the output with the atom sort of in the center and try to determine what an atom really looked like inside. Imagining, of course, that it would be a sort of plum pudding solid structure like J.J. Thomson had said. So what Rutherford designs is an experiment where he shot alpha particles. They're basically helium nuclei, we know now, and they're small positive particles. And he shoots them at a sheet of gold foil. So gold can be sort of rolled out really, really super thin. So the foil itself was just like a few atoms thick. And what Rutherford imagined would happen is that if Thomson and Dalton were correct, then atoms were made of this sort of solid stuff. So either all of the particles would pass straight through the atom, so if it was sort of a soft stuff, they would pass straight through, or if the atom was really solid, like a marble, you can imagine, then all of the alpha particles would go into the gold foil and hit an atom and bounce straight back. So that was what he expected. So he thought that 100% of the alpha particles shot at the gold foil would behave in exactly the same way. So it would either all go through or all bounce back. So here's a picture of the setup. You can Google if you want gold foil experiment, and you can probably find like a cute little animated version of this. But basically you have the alpha source here. It's shooting out alpha particles at this piece of gold foil. And alpha is one of the types of decay that naturally happens. So there would be something inside the box that was naturally undergoing alpha decay. And then around the outside is some photographic film. And so when the alpha particles hit the film, they would expose it and leave a little dot. And it was much more enclosed than this picture shows to really get all of the alpha particles results. So, the results. What ended up happening was that most of the alpha particles passed straight through the foil, which was not unexpected, right? Rutherford thought that likely they were going to just pass straight through. However, a small percentage of the particles went through the foil. So if you imagine, here's your foil. They went through the foil and then were deflected at an angle. So they didn't go straight through, but they went through and turned. And then the last bunch sort of went into the foil, but then bounced back toward the source. So this was not what Rutherford had expected. Remember, he thought that every single particle was going to behave in the same way. So what Rutherford said about this was that it was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. These results were completely surprising. Rutherford was sure that Dalton and Thomson were correct. He was sure that all of his particles were going to behave in the same way, and they just completely did not. They behaved in 3 very different ways, especially compared to what Rutherford had initially expected. So as scientists, it's important to remember that even though we kind of might have an idea of how an experiment might turn out, you need to go into things with an open mind because your results might be totally different than what you expected. So once Rutherford got these crazy results, his next task was to interpret them. So he looked at each group of alpha particles and sort of tried to figure out what that behavior meant about the atom itself. So first of all, he said that the particles that passed straight through indicated that the atom wasn't solid. It must be made up of some empty space, a lot of empty space, because a lot of particles pass straight through. For the particles that deflected at an angle, Rutherford said that they must have gone into the gold foil, but then ricocheted off of something that was very dense by a slight glancing blow. If you imagine like a pool ball, like the cue ball coming in and hitting a pool ball and then it going off in a completely other direction, it's that kind of idea. Alpha particles, so those particles that were shot into the gold foil, we know that they have a positive 2 charge. And so what Rutherford said, knowing what he knew about electrons from Thomson, and negative and positive charges generally, he said that that positive charge must have come close to something else that also had a positive charge, because positive and positive would repel. So if you imagine within the foil, there's these positive charges, and then the alpha particles, which are also positive, come in. They're positive and positive, so they repel that way. So with the last group of particles, the particles that bounce straight back, he said that they must have had a collision with something much more massive than the alpha particle. And the alpha particle, they knew at the time, had a 2+ charge, as we said, and it has a mass of 4. Mass of 4 that comes from 2 protons and 2 neutrons. So that's a 0 because neutrons are 0 charge. Okay, so if they bounce straight back, you had the positive foil, and then these little tiny alpha particles were going in and then bouncing straight back again. So Rutherford's interpretations didn't really explain why so few alpha particles were deflected. So he kind of had to put all of his inferences together to come up with this final understanding. So what he inferred from the numerical data as well as from the observational data was that the very dense thing in the center that was positive was very small in comparison to the rest of the atom. So for the most part, the alpha particles would just pass through, but if they lined up just right with that positive center, then they would either bounce right back or be deflected. So this all together leads to Rutherford's model of the atom. So Rutherford's model is probably fairly familiar to you. It is at least part of the model that we still use today, and that is the nuclear model. So the nuclear model was that, or is that, the atom itself is mostly empty space with a dense, positively charged nucleus at the center. So that we know now is where the protons and neutrons are located. Remember, they didn't know about neutrons at this point yet. And then he knew that electrons, those negative particles that Thomson had discovered, were around the outside. Rutherford didn't really worry about, like, giving structure to the electrons or anything, but he knew that they were there, right? So, what Rutherford's model, like, we still understand that the atom has a nucleus, that it's positively charged, so we've kept a lot of his discovery till now, but it didn't explain what kept the electrons, the negative electrons, from just sort of spiraling down and collapsing into the nucleus, because positives and negatives attract. And so what was going on to keep those electrons outside the nucleus? Because we know that that's where they are. We know that they're separated because electrons can move around and react, but we don't know how. So one of Rutherford's students was Niels Bohr, and he's a gentleman that we'll talk about several times over the next week or so. He thought he could answer the question. What he said was that just like centripetal motion, so the speed of going in the circle, counteracted by the pull of the nucleus, just like planets orbit the sun and they stay in their orbits because they're going fast enough to counteract the gravitational pull of the sun. So just like that, that must be what's keeping the electrons in their orbit as well. The electrons are going fast enough that they just keep orbiting, and they stay in the orbit because the nucleus is still holding on to them and pulling them. So Bohr updates the model. He adds some electronic structure to Rutherford's nuclear model of the atom. And this is the model that you've probably seen many times in your life. So you have the nucleus in the center, and then these electron shells surrounding it, and each one can hold a particular number of electrons. And electrons just stay in their little orbit, just like planets orbit the sun. So sometimes it's called the planetary model, you'll see. So this was in about 1914, so you can imagine World War I is sort of just on the horizon, and a lot of technological advancements are still in the offing. Bohr's model had some support sort of from an unrelated field, and that was optics, or the study of light. So there was a guy named J.J. Balmer, who was a high school science teacher, and he had studied the line spectra. So this is a line spectrum. It looks a lot like a rainbow, but it has these bright, distinct bands in it as well. And so those bands are given off specifically by a hydrogen atom. And so what Balmer did was he came up with an equation that fit these particular wavelengths of light. If you remember from your previous science, the wavelength of light corresponds to the energy of light. The lower the wavelength, the higher the energy. And the longer the wavelength, the less energy. So this would be the low energy side. This would be the high energy side. So Balmer came up with this equation that fit the wavelengths of the lines. And then Bohr's model, when he was looking at those particular orbits, likewise had electrons with lower energy and then with higher energy that fit with what Balmer had seen. So these two seemingly disparate things were kind of supporting and lending credence to one another. We'll talk a little bit more about what this line spectrum is and what causes it as we move through the week. So Bohr said he found that his model of orbits matched with what Balmer had seen. And so what Bohr surmised was that if an electron fell from a higher orbit to a lower orbit, I'm just drawing some orbits here, that it must give off energy. And so the distance between his orbits matched that light that had been seen by Balmer. So let's say we have an electron that's excited up here, and it makes a little fall, so a low energy fall, because it's just going a short distance. Then Bohr said it must be giving off red light, so it's a small fall. If the electron then fell the rest of the way down, that's a little bit bigger distance, so it's going to be a little bit more energy. So maybe that's going to be a green light given off. If it were to fall down the entire way, the whole double step at once, maybe that would be blue light, which is even higher energy. So those energy distances matched with Balmer's light wavelength distances. And so this seemed like Bohr was on a really good track. So tomorrow, or Wednesday, we will talk about what happened sort of from here, from Bohr's planetary model, and how it needed to be adjusted a little bit further to get us to the final model of the atom that we understand today.